So in this last section of Unit 6, we're going to take a look at the average value of a function, and we've dealt with this previously when we were working with integrals and particle motion, but we're going to try to relate average value to any function, not necessarily just velocity or acceleration. So if we actually kind of pick apart the phrasing of average value, we've seen the word average before in terms of like average rate of change, and that normally means that we're going to be calculating something over an interval where you need like a beginning spot and an ending spot to help you with that calculation. In terms of the word value, if we're looking for the value of a function, that's basically an output or an answer or a y value, okay, all these synonyms. So basically when we're finding the average value of a function, we're finding the average output on some interval that a function would produce. So if we think about how we've calculated average velocity in the past, notice how we would be calculating something over an interval. So we need a beginning point and an ending point, and those 2 points that we use to help us calculate velocity happen to be 2 points on position. And we typically find the slope between those 2 points. So slope between 2 position points. If I write that out mathematically, maybe I'll take the position at time B, and then I have to take the position at time A, so this is my change in y values, and I have to divide the change in the respective x values, so that would be B minus A. All right, so slope between 2 points on position would give us average velocity. Very similarly, we can do average acceleration. So this would be the slope between 2 points. But if we're calculating an average acceleration, we would have to need 2 points on velocity. So if I wrote it out mathematically, I would need a velocity value at some point minus a velocity value at another point, and I'll divide that by the change in respective x's. All right, so this is how we've calculated average velocity and average acceleration in the past. We're going to see how we can still calculate average velocity and average acceleration, but notice how in the past, in order to find average velocity, you had to know position, and in order to calculate average acceleration, you had to know velocity. The question is, what if we don't have either one of these available? For instance, what if we didn't know position? How could we still calculate average velocity? And what if we didn't know velocity? How could we still calculate average acceleration? So we're going to take a look at kind of these two integral setups here to see if we can approach this average value or this average output a different way. So if we're going to integrate acceleration, that means we're going to work backwards. And notice how our bounds are from A to B. So if I want to work backwards from acceleration, that's going to give us velocity. And I can do the top bound of B minus the top bound of A. So typically we'd stop at this point when we just have kind of a regular integral, but notice how this one has something extra out front where we are multiplying by 1 over B minus A. And notice how B minus A just represents the difference between these two bounds. So I'm going to take this antiderivative from acceleration, and if I multiply it by 1 over B minus A, I'm essentially going to have B minus A on the bottom. And notice how this is exactly what we said previously represented average acceleration. So instead of using 2 points on velocity to help us find acceleration, we could essentially integrate the acceleration function, if we had that available to us, and divide by the change in the bounds, or the difference of the bounds. Very similarly, we can do something for velocity. So if I work backwards from velocity, that's going to give me position. So top bound minus bottom bound. And again, I'm going to divide by this change in the bounds, this B minus A. And notice how this is what we said previously, represented average velocity. So instead of having to use 2 points on position to help us get average velocity, notice how we can integrate a velocity function if we have velocity information available to us instead of position information. So we are starting to have a different method or a different technique, or just at least a different way for us to calculate average velocity and average acceleration, because these two up here depended on knowing position for velocity and velocity for acceleration. And in this case, if we want to utilize integrals, if we want to find average acceleration, we simply just have to know the acceleration function. Similarly, if we want to find average velocity, we would just have to know the velocity function. So we can kind of generalize this. If we wanted to find the average output of any function, no matter what that might be, it seems like we need a particular setup of 1 over the difference of the bounds times an integral from a to b. And if you want the average value of some function, that's the function that you need to work backwards from, aka that's the function that you need in your integral. Again, notice how average acceleration utilized acceleration and average velocity utilized velocity. So we're just going to take a look at some examples, not necessarily related to particle motion, but just any function in general. So we want to find the average value, aka the average output that this function would have on this interval. So if we think about it, we're going from 1 to 3. And out front, we got to multiply by 1 over the difference of the bounds. So there are 2 units between 1 and 3. And if I want to figure out the average value of this function, that's the function I'm going to utilize within my integral setup. So I don't necessarily feel working backwards from this by hand. That's why we're going to kind of utilize a calculator to help us with this. Alright, so if I type in, let's see, I have a 1/2 out front, so I'll do 0.5, and then I'll do math 9 to bring up my integral from 1 to 3, and I'll type in my function. So to 4 decimal places, 5.848, you can chop it 1 or round to 2. All right, now this is our average output that this function would have on this interval. So there are some numbers that are going to be less than this as y values. There are going to be some numbers that are bigger than this as y values, but this is the average. Let's maybe try to do one that's not calculator. So we'd have to do this one by hand, find the average value of this function on that interval. So we're going from 2 to 6, and the difference between the bounds is 4, so 1 over 4 out front. And I'm going to work backwards from 2 minus 4x. All right, so I have the 1/4 out front. And then I need to work backwards from this function. So using my reverse power rule, I'll have 2x minus 2x squared. And my bounds are from 6 to 2. All right, so if I start to plug things in, 2 times 6 would be 12. If I square 6, that'll be 36. Double that, we'll get 72. So 12 minus 72 would be negative 60, and if I divide that by 4, I'm going to have negative 15. So if I plug in 6 into everything, I'm going to get negative 15. I then have to subtract what I get when I plug in 2. So I'll have 4 here, and then 2 squared is 4, times 2 is 8, so 4 minus 8 is negative 4. Divided by 4 would be negative 1, and if I'm subtracting that, it's going to change to a plus 1. So it looks like my average value is 14. Okay, so like I said, there are some numbers that you can get out as y values that are bigger than negative 14, smaller than negative 14, but this is your average. All right, let's maybe revisit particle motion. We're going to find the average velocity of the following particles, but notice how even though the equations are the same, they represent something different. So for part A, we're going to let this function represent position, whereas in part B, even though it's the same function, it represents velocity. So depending on the information we have to think about how we're going to use that to calculate our average velocity. So if we have position, we could use our average velocity definition as slope between 2 points on position. So if our interval is from 1 to 7, I'm going to have to get a point at 1 and get a point at 7. So let's see, if I plug in 1, I'll get negative 125, and if I plug in 7, I'll get 49. So I need to find the slope between those 2 points. So change in y's over change in x's. Let's see, this would be negative 174 over negative 6. So overall, positive 29. Here we go. Let's say, however, that we want to find average velocity, but this time our function we're utilizing actually represents velocity, okay, the average value of the function that we have. So in this case, we're going to use our integral definition of average value, where we're going to integrate on the interval, and if we want to find the average value of the function we have, we're going to use that function inside the integral notation. We also need 1 over the difference of the bounds out front. So my integral setup would look like from 1 to 7. If I want the average value of velocity, I'm going to use the velocity function within the integral. And I need 1 over the difference of the bounds out front. So there are 6 units from 1 to 7. All right, we're definitely going to utilize a calculator for this one. So let's see, if I clear this out, I need 1 over 6 out front, math 9, my bounds are 1 to 7, and the function I want to find the average of, I'll just type it in. Looks we got negative 119.6. All right, so notice how both of these are average velocity values, but the function that we used represented something different in each case. So depending on if it's position or velocity, we have to kind of be familiar or think about, are we finding kind of a slope value or are we finding an integral value?